Going to start. Welcome everybody to this is the first presentation of in Colegio Castlefield with the Nobel Laureate. We are presented today, presented by Nobel Laureate School Outreach, and I will give the word to Arturo Minuti, who is the principal across all the school in the Colegio Castlefield. Arturo, if you can, please. And then after we go that, we're gonna go. This is gonna be this is the agenda, for everybody can see the different times. We plan to do it right now, 11 a.m. Puebla, noon in Massachusetts, and then we're gonna move along. We expect to finish by 1:40 p.m. Eastern, 12:40 Mexico time. We're gonna be Arturo gonna give us a welcome message. Gonna go to the introduction of the panelists by Pelayo, who is the principal of high school. We're gonna have the introduction of Dr. Sheldon Glashow by Dr. Edward Shapiro. Dr. Glashow's presentation will begin at 12:15 Eastern time. We're gonna continue right after with questions and answers that the students of Colegio Castlefield have been provided, and they're gonna be reading them at time. And then at 1:20, we're gonna have a panel with Dr. Glashow and some students that have been achieving great results at the school. Finally, Arturo Minuto will provide a wrap up, and we will end up and close the session. Arturo, without being alive, can you go ahead and please start?
Thank you, Manuel. Good morning, everyone. My name is Arturo Minuti, and on behalf of the Board of Trustees of Castlefield School, we warmly welcome to our conference with the Nobel Laureate, Dr. Sheldon Glashow. It's an honor and a privilege for this community to be able to have an event like this. I would like to thank Manuel and Mauricio Barroso in a very particular way for making this event possible. It's an honor to have people like you in our community. I would also like to thank our panelists and in general to all our students and parents that will join us. Without further introduction, I leave you with the high school director, Pelayo Fernandez Huerta, who will introduce today's panelists. Thank you.
Good morning, Dr. Sheldon. It's a pleasure for me to introduce the panelists. Margarita García Rojas, ingeniera agrónoma fitotecnista, con especialidad en cultivo de tejidos vegetales, de la UPAEP. Natalia Toski Márquez, alumna del área de ingeniería. Daniel Pérez Olmedo, médico veterinario zootecnista de la UNAM, con inclinación formativa en conservación de fauna silvestre. Maximiliano Roldán Pimienta, alumno del área de ingeniería. Eduardo Leiva Martínez, alumno del área de ingeniería. Estudiante Juan Carlos Galina Migueles y estudiante Mauricio Barroso Jiménez. Thank you for your attention.
Dr. Shapiro, thank you. And if you could have introduce yourself as well as Dr. Glashow.
The Nobel Laureate in Physics, Professor Dr. Sheldon Glashow, Colegio Castlefield School White Principal Arturo Minuti, High School Vice Principal Pelayo Fernandez, School Advisor Mauricio Barroso, dear students, the honorable guests, good morning. My name is Edward Shapiro. I represent the Nobel Laureates School Outreach, a non-profit corporation bringing Nobel Laureates in all 6 fields to inspire high school students around the world. It is my honor to express our deep gratitude to you for supporting Science Festival's founder, Manuel Barroso, and Nobel Laureates School Outreach for bringing the Nobel Laureates tradition to your beautiful country and beautiful town of Puebla. As you all know from Dr. Glashow's autobiography, he graduated Bronx Public School of Science, which gave mankind eight Nobel laureates, 7 in physics and 1 in chemistry. So far, your beautiful country, Mexico, gave already 3 Nobel laureates in Peace Prize, literature, and chemistry. Today, Nobel laureate Glashow is a living example, giving us a new challenge to follow in footsteps with his Bronx School of Science. Let us give a strong round of applause to Nobel laureate role model, Dr. Sheldon Glashow. Welcome, Professor.
Thank you so much.
Thank you, Ed.
Really appreciate it. And thank you, Ed. And the floor is yours, Dr. Glashow.
Thank you.
It's a great pleasure to be back in Mexico, virtually. I have a long history in Mexico. I attended the first Latin American summer school in Mexico City in 1955. And just last year, I was honored to receive an honorary doctorate from the Autonomous University of Chiapas. Now I'm back in Mexico. Let me begin when I was a long time ago, in junior high school in the 1940s. And at that time, I think is when I became interested in science. So many things having to do with science were in the news. The atomic bomb had exploded in 1955, whatever it is. Radar was developed. The V2 rockets had been demolishing much of the English cities. Penicillin had been widely deployed. Jet aircraft were first used by the British and by the Germans. And television had emerged as a commercial enterprise. And in fact, we bought our first television set in 1947. So much was going on. So I was deeply involved in reading science fiction. And between science fiction and the news about the role of science in the war and afterward, confirmed my interest in science, whether it was biology or chemistry or physics was not yet clear to me. However, I decided to go to the Bronx High School of Science, a public school, from my public junior high school. So off we went. A number of my friends from the neighborhood also went to the Bronx High School of Science. Others went to different high schools in New York. I came to Bronx Science and I made a number of friends rather quickly, and many of them became well-known scientists. Just a few were Gary Feinberg, who was a dear friend of mine. He lived also in Bronx in New York City. I lived in Manhattan. We tried to compete, trying to learn all kinds of physics that we were prematurely studying. He remained my friend until his tragic death when he was in his 60s. Dan Greenberger, he taught me calculus in the school lunchroom. Morton Sternheim, with whom we started a science fiction fan magazine. Henry J. Stern, who would become the Parks Commissioner of New York City. It was a very impressive bunch of kids. And many of us decided to go to Cornell. Among them were Kent Gordis, Dan Filson, two now deceased students of physics who became quite successful, and Steve Weinberg, with whom I would share the Nobel Prize much later, 30 years later, in 1979. So Steve and I and Gary were focused on elementary particle physics. We wanted to follow in the steps of people like Albert Einstein, one of our heroes, and the first winner of a Nobel Prize in physics by Japan. In fact, it was the first Nobel Prize of any kind that Japan won, was the prize to Yukawa. And we went to a lecture of Yukawa in New York soon after he won his Nobel Prize in 1949, just before we went off to Cornell University. So at Cornell, we had Steve and I had looked at 3 different schools. We looked at Princeton and MIT and Cornell, and both of us chose to go to Cornell because it was so beautiful, idyllic, in fact. Hit the city on a hill, beautiful. So we studied physics, and when we left, we were ready to go to graduate school. Steve went to Princeton. Gary had not gone to Cornell. My friend Gary Feinberg, he went to Columbia, stayed there for the rest of his life as a distinguished professor. And at Cornell, I decided, well, I had an experience of taking lots of courses that I was not prepared for when I was at Cornell. One of them I failed. I failed a physics course in my junior year. I was quite embarrassed by that. But nonetheless, I went to Harvard and found a very happy graduate experience at Harvard. I spent 4 years at Harvard. Some of my friends at Cornell did other things. Gary Neugebauer married one of his classmates, both of them physics majors, and they went off and had wonderful careers in astrophysics. Another of my female students, classmates, Tema, married her instructor and became the wife of a distinguished professor at Harvard. Jerry Sachs was thrown out of school for cheating, but he became the only full professor jointly at Harvard and at MIT of mathematics. And Danny Kleitman was with me too. He became a famous mathematician as well. So many of my classmates became quite well-known scientists. We went to Harvard, and at Harvard, after a year of taking courses, I wanted to become a student of the Nobel Prize winner at Harvard, Julian Schwinger. And 10 of us went to him, 10 or 12 of us at the same time, and wanted to be students. And he accepted us all. And I can remember some of them offhand. Danny Kleitman, he became a mathematician, and my brother-in-law, Ray Sawyer, he became a professor at the University of California. Another became a professor at the Illinois Institute of Technology, another Yale, another NYU, another at the University of Washington. These were all my contemporary students, my friends at Harvard. After 4 years at Harvard, I decided to go as a postdoctoral fellow to the Soviet Union. And I was all set to do that, but I never got a visa. So instead, I went to Copenhagen to study at the Niels Bohr Institute in Copenhagen. Let me say a word about my thesis. The thesis that was assigned to me, I was the last online of the students. My advisor, Julian Schwinger, had run out of solvable problem. So he gave me a problem that I could not solve, which was to unify the weak and electromagnetic forces. There were at that time 4 independent forces of nature: gravity, electromagnetism, and 2 nuclear forces that Einstein never recognized: the strong nuclear force and the weak nuclear force. And Julian told me to unify the weak and electromagnetic interactions, and I saw that there must be such a theory, but I couldn't find it. Not until I went to Copenhagen as a National Science Foundation fellow, supported by the American government, and unable to go to the Soviet Union. Nonetheless, there I wrote the paper that would win 1 share of my Nobel Prize many years later. The paper was written in 1960, the Nobel Prize in 1979. After I spent 2 years in Europe doing interesting physics and writing the paper that would win the Nobel Prize for me, I was lured to California by Murray Gell-Mann, another Nobel Prize winning physicist, to Caltech. I spent just 1 year at Caltech. There was no faculty position available, so I moved on to Stanford, but there was no possibility of a tenured position at Stanford, so I moved on to the University of California, where I thought I would remain. It was a very lovely place to be until I was called back to Harvard. And I became a professor at Harvard in 1966, spending 34 years as a Harvard professor. And much of that time I was married and I was bringing up a family here in this very house in Brookline, Massachusetts. And eventually I decided to leave Harvard and go to a school where I could walk to work rather than drive to work. And that's Boston University, which is just around the corner, a 10-minute walk to my office. Of course, I can't go to my office right now for the same reason that my kids cannot go to college, because we're in the middle of a pandemic. And that's why I do things like this when I have no other opportunities of visiting schools or visiting universities or collaborating with other scientists or hugging my grandchildren, who I cannot access because they don't live here. They live in California, Virginia, New York, etc. So let me tell you about my final exam that I took from Harvard before I went to Copenhagen. To get my thesis, I had to take an exam, and there were a number of distinguished people on my committee, my examination committee. One was, of course, my advisor, Julian Schwinger. Another was another Nobel laureate who was Frank Yang, and of Yang and Lee, a very famous physicist. And we had an interesting altercation at that time, which was where he was puzzled by something I was trying to say. I couldn't answer it, so my friendly thesis advisor, Julian Schwinger, satisfied Professor Yang, and then Yang was satisfied with me, and I received my degree. The reason I mention this story is that a year later, Mr. Yang, together with Mr. Lee, both of them Nobel laureates, published the solution to the little puzzle that Julian Schwinger had provided. So they stole the idea. Anyway, off I went to Copenhagen, and from Copenhagen to Caltech, and from Caltech ultimately to Harvard. And my time at Harvard was perhaps the most exciting in physics, in my field of physics, since the 1920s, when quantum mechanics was developed, because so many challenges in physics were met during those years. And I was pleased that I was part of the story of developing what's called the standard model of elementary particle physics. And in order to do that, I had to collaborate with other people, and we played a small role. But what I'm trying to emphasize is how important international collaboration in those days and always in physics had been. I mentioned to you my various experiences in Mexico, but I've had many, many important occasions to be in Europe, to be in different countries in Europe and Asia, Japan, China, Korea, etc. And my collaborators at Harvard, the three most important collaborators were Alvaro de Rújula, a Spaniard, John Iliopoulos, born Greek, but he became French and is a very distinguished French physicist, and Luciano Maiani, who is, of course, Italian. Collaboration, international collaboration is central in physics. So what's next? What's next is I'd like to try to convey to you the enormous excitement of the 1970s when I was at Harvard. It started actually in Copenhagen again in 1964 when I was on leave in Copenhagen, and one of the greatest physicists, I say that because he's 6'7" high, he's well over 2 meters, and he and I introduced the fourth quark, the charmed quark. That was in '64, and eventually the charmed quark was found, and that took until another decade, until 1974. When the charmed quark was found, well, how was it found? It was a day I will never forget. It was in November of 1974. I was sleeping, telephone rings. This was 5 years before my Nobel Prize. It was Sam Ting, an experimental physicist, also a Nobel Prize winner at MIT. He called me to tell me he found a new particle. And very soon I realized that that new particle was made of the charmed quark and its antiparticle, the charmed antiquark. And it was made of these two particles, quark and antiquark, going around each other, just like positronium, which is an atom made of an electron and a positron going around each other. And Alvaro named that forevermore charmonium. And we worked for a long time on trying to understand the spectrum of this curious animal. Anyway, time passed and the standard model grew and it became generally accepted. And today we are very proud. Many, many physicists contributed to the creation of not just the unified theory of weak and electromagnetic interactions, but a theory of all interactions excluding gravity called the standard model. And so far as we know, that standard model remains totally correct and exact even today. And one of the great frustrations, aside from the pandemic is stopping most everything in science from happening. The large accelerators that exist at CERN have shut down and people are not allowed to participate. CERN is the world's leading particle physics laboratory today. And these experiments in the States, in China, in Japan, have all stopped for the moment, as everything else has, while we wait for the vaccine to be invented to deal with the pandemic. I'm sure it's troubling Mexico as it is troubling the United States. In any case, that brings us to now. The standard model has been created, over 20 years ago, 25, 30 years ago. We still have not created a theory to replace it, although my friends, the string theorists, have tried and failed. So we need more people, and perhaps someone listening to me now, someone in Mexico, will have the ideas that will lead us to more successes and more triumphs and more excitement in my field of physics. Thank you all very much for listening. Okay.
Thank you so much, Dr. Glashow. Really appreciate it. It was very enlightening. I think we want to proceed now with the questions and answers that were submitted ahead of time. And later on, during the panelists, we're going to respond the questions that come to the Q&A button. Okay.
Excellent. I look forward to answering the questions.
Yeah, Pelayo, do you can turn on your camera, please? So you can go ahead and Margarita. Yeah. Now Margarita gonna help us to guide through the questions, and gonna be guiding the different people. Pelayo, do you mind to reintroduce again the panelists so people understand now in the full community who is the professors and students asking the questions?
Santiago Galvan, your question, please.
Okay, so hello, Dr. Glasgow, Dr. Shapiro. My name is Santiago Galvan. I am a panelist. I wasn't introduced in the section, but well, I will introduce myself. I am a student. I was a student of nanotechnology in UNAM. I was specialized in physics of nanostructures, and I am a fan of your work, and I like your investigations. And well, these are my questions. Okay. So first, why particles must have a left-hand chirality and antiparticles a right-hand chirality to interact with the electroweak force?
That is, of course, two questions, not one. The first question is, why is it that left-handed fields of particles participate in the weak interactions? Well, they in the weak interaction, not the electroweak. Any charged particle is involved in the left and right in the electromagnetic part of the electroweak theory, but only left-handed fields participate in the weak interactions, and that is a mystery that we do not understand. It's part of the structure of the theory. The second question has to do with the fact that antiparticles. It is the right-handed component of antiparticles that participate in the weak interactions. And that's a mere consequence of the notion of antiparticles, because all of the properties of antiparticles are diametrically opposite to the properties of the corresponding particles, except the mass. So for the electron, it's the left-handed electron that participates in weak interactions, and for the positron, it's antiparticle. It's the right-handed positron that participates, but that's merely a necessary consequence of the nature of antiparticles.
Okay, thank you so much. The next question is, are neutrinos Majorana's particles?
Well, Majorana did not predict the existence of neutrinos. That was done by Pauli in 1930, when in Christmas of 1930, when he was unable to go to a physics conference because he was more interested in going to a dance in Switzerland, he sent a letter to Germany, which solved several problems at the same time, and that involved the predicted existence of particles that became known as neutrinos. Now, neutrinos can be of one of two sorts, or something in between. One is called Fermi neutrinos, and the other is called Majorana neutrinos. And it seems that we don't know the answer to that question yet. That's a very interesting question. It revolves around the question of whether lepton number is conserved, and it will be answered by the observation or non-observation of what's called neutrinoless double beta decay. And those experiments are at the required sensitivity are being carried out today, except for the pandemic.
Okay,
we will know about that within a couple of years.
Okay, I think that's very interesting. And well, next I have, how did you realize that the electromagnetic and the weak interaction was in fact unified? How was your thought process?
I didn't have to think. When I interviewed Schwinger at the beginning of my doctoral research, he told me that I should think about the possibility that the weak and electromagnetic interaction should be unified. He pointed out two indications that there should be such a theory. One is that the so-called universality of weak interactions mimicked the universality of electrical interactions. And furthermore, the vectorial nature of the weak interactions mimicked the vectorial nature of the electromagnetic interaction. And yet the weak interaction was very, very weak, and the electromagnetic interaction was quite a bit stronger. So some things were similar, some things were very different. Could I explain how the theory could be unified? And I spent the 2 years working on that. I got nowhere. I went to Copenhagen, and where I found part of the answer in 1960. I can't tell you what the thought process was, but the realization was that the mathematical structure that Schwinger was contemplating was too simple. It had to be replaced by the next most complicated, one slightly more complicated mathematical group.
After the panelist questions, Dr. Glasgow will answer the public questions, okay? Next question is, what theory, other than the Standard Model, can explain the existence of dark matter?
Okay, I have to fix that question because the Standard Model does not offer a solution to the problem of dark matter. It would have if neutrinos had been heavy enough, but they are not. And there are no particles within the Standard Model that could possibly explain dark matter. So dark matter has to be something else. And for many years, physicists have been preoccupied with particular theories called technicolor, which was shown to be inadequate, and supersymmetry, which has also been shown to be inadequate to offer a solution. So it has to be something else. And we don't know what that something else is. It could be a particle of some sort. It could be a very heavy particle, or it could be an exceedingly light particle. And that would be called the axion that had been suggested by a fellow Nobel laureate, Frank Wilczek. We don't really know, and experiment will give us an answer one of these days. Not yet.
That's good. Thank you. Next question, Danny, please.
Okay. Hi, Dr. I have two questions. The first, what does SU means? And what are the difference between SU 1, 2, 3, and 5?
That's easy to answer. The SUN, where n is a positive integer, 1, 2, 3, 4, etc. SUN is the group of n by n matrices whose members are both unitary and unimodular. Unitary means that any such matrix multiplied by its Hermitian adjoint gives you the unit matrix. Unimodular means that these matrices have determinant of 1. So SU1 is trivial, it's just the unit matrix. SU2 turns out to be of the same form as the rotation group in 3 dimensions. And SU3 is unitary group of 3 by 3 matrices, which is the underlying group of the strong interactions, what the theory called quantum chromodynamics, et cetera, et cetera. SU5 was the first suggested version of a grand unified theory that would explain weak, strong, and electromagnetic interactions. The theory doesn't work very well. Anyway, they just have to do with matrix groups, Lie groups, which for reasons that string theorists claim they understand, must underlie the fundamental interactions of nature.
Thank you, Doctor. Next question, please, Annie. Max, Natalia. Natalia, is your turn.
Yes. Is there evidence for another interaction between fundamental forces besides electromagnetism and weak force?
Well, yes, gravity. The gravitational interaction is another interaction besides electromagnetism and the weak force. The question that makes basically 4, electromagnetic and weak are combined together, just as electromagnetism combines electricity and magnetism, that's 2. And there's gravity and the weak interactions, that makes 4. Can there be a 5th force, a so-called 5th force? Well, people have looked very hard for it. Occasionally, people would claim evidence for such a 5th force, but at the moment, there is no decisive evidence for any such 5th force. We shall see. There are lots of unanswered questions.
Okay, that's good. Max, is your turn, please?
What are the fundamental forces and why are they so important?
Oh, well, I mentioned what they are, but let's say the electromagnetism is important because otherwise the sun would not be able to send us its energy. We would not be able to see, etc. Clearly, evidently very important, but even more so, without electromagnetism, there could be no atoms because it is electromagnetism that holds atoms together, and it is electromagnetism that leads to the chemical force between different atoms. So there would be no chemistry and no atoms, no molecules, nothing. So it's clearly very important. The strong force is very important because the strong nuclear force, it holds nuclei together. If it did not exist, there would be no force between neutrons and protons. In fact, there would be no neutrons and protons at all, because it is the strong force that holds quarks together to yield the neutrons and protons, and it is a pale residue of the strong force that leads to the nuclear force between protons and neutrons. So not only no atoms, but no nuclei if the nuclear force was not there. And the last of the 4 forces of gravity, and if gravity did not exist, the oceans would not stay in the ground, and the earth would not go around the sun, and we would not be here. Got it? Those are the 4 forces and why they are all important to us.
Thank you, Doctor. Now, let's go with Eduardo, please.
In your opinion, what will be the next step in the standard model?
Oh, I have no idea. The next step might be the result from some experiments, passive experiments, as we shall discuss in a moment, could result from the observation of neutrinoless double beta decay, could result from the discovery of the particle or the mechanism that's responsible for the dark matter of the universe. An explanation also is missing for the dark energy of the universe, which is presumably due to Einstein's cosmological constant, but that has not been proven as yet. There are many things that have to be done. Another is to determine the origin of neutrino masses, because another thing that is missing from the standard model is the mechanism by which neutrinos acquire their mass. And since 1998, we have known that neutrinos do have mass, but very small masses. So lots of steps can be made and may be made, remain to be made by experiment. It is experiment that will lead us to the next development of the theory.
Oh my God. Okay, follow with next panelist, Santiago, please.
Okay, what is passive experimentation and why is it important in science study?
Well, science, let's change science to my discipline, which is the fundamental questions of what matter is made of, elementary particle physics and such. Because in biological science, it's obvious that experiments are necessarily passive. What you mean by passive experimentation is not using accelerators, doing physics without particle beams. Most of what's been discovered, for example, the discovery of the antiproton, the observations of quarks, the astounding discovery of the Higgs boson in 2012, all of that was done with accelerators. However, many other experiments are done by observing nature, such as cosmic rays. It was cosmic ray experiments, for example, that led to the discovery of the positron, that led to the discovery of strange particles. We also, and also that the discovery of the violation of space reflection symmetry in the 1950s, the violation of, that was not an accelerator experiment, that was the study of radioactivity. And there are many other experiments that remain to be done at high precision, such as the search for the electric dipole moment of the neutron, which has not yet succeeded in finding its value because it's too small. And the search for dark matter and the origin of dark energy, the nature of the origin of the universe, all of these astronomical observations, those are passive. We're not banging particles against one another. We are observing what nature presents to us.
Thank you.
Good. Okay, in some of your talks in your youth, you mentioned the subway as a place of study. Why?
Well, every day I went to school at the Bronx High School of Science. I had to get there. I couldn't walk. So I would either take a bus, take a subway, or occasionally when I was late, take a taxi, which I would share with 4 or 5 other kids because it would otherwise be too expensive. But normally I took the subway, and in the subway I spent some time, maybe 20 minutes each day with my best friends, Feinberg and Weinberg, who both lived in the Bronx and also took the subway to get home. I had to take the subway in the Bronx and then connect to a subway in Manhattan to get to my home. So we had every day a little confrontation. What did you learn yesterday and outside of school? And we would compare notes so that the next time we could brag about something else. It was a time to discuss what we were interested in outside of class. That makes a point, and the point is that throughout my life, I feel that I've learned at least as much from my peers, my classmates, whether it's junior high school or college or graduate school. I've always learned more from my classmates than from my teachers. Sometimes in the same way.
So interesting. Thank you, Doctor. Okay, Danny, is your turn, please.
Thank you. Doctor, we have read about your opposition to string theory. What things you think are inconsistent?
Nothing is inconsistent about string theory. The only problem with string theory is that it cannot be proven to be, no experiment can confirm it or no experiment can falsify it, can show it to be wrong. It makes no explicit predictions. It says that things are the way they are, and by things I mean the nature of the standard model, the masses of the quarks, the masses of the electrons and other particles, neutrinos, the forces between them, the nature of the mathematical structure of the standard model. All of those questions cannot be answered. They are the way they are because this is one universe out of an infinite number of universes. So we live in the best of all possible worlds.
Thank you.
Thank you, Doctor. Natalia, is your turn, please.
Yes. Currently, the work of women in science is beginning to be recognized. Can you mention some of them that are important in the field of theoretical physics?
Yes, theoretical physics and the mathematics that underlies theoretical physics. Yes, indeed. Let me merely mention that, well, let's see, how can I say this? I have had not very many students in my life. I've had about a dozen, not more than that, maybe 13. And the last of them, the 13th, was a young lady who became a professor of astrophysics at Penn State University, Ruth Daly. So I've had just one female student and a very successful one. My colleague at Harvard, Howard Georgi, has had a lot of women graduate students. I counted up about 8 of them, all of them successful theoretical physicists. One, her name is Miss Dawson, and she's at the Brookhaven National Laboratory. Then there's Eva Steinberg, who is at Stanford University. I have them listed someplace, but the names don't matter. He's had about, one of them you have heard of is what's her name? The one at Harvard. A name slips my mind at the moment, but yes, there have been a number of important theoretical and experimental physicists in particle physics. A very great mathematician, the first female winner of the Nobel Prize in Mathematics, the Fields Medal. She was the first woman was an Iranian woman. It was also the first Iranian to win the Fields Medal. She died, sadly, of breast cancer at a very young age, at the age of 40. But she was a magnificent theoretical mathematician and physicist. So yes, women have very much moved into, the Harvard lady, by the way, has also written 2 operas just to show that there is no barrier between the arts and the sciences. And her opera was presented in Madrid and also in Paris. So yes, the women are coming more and more into science, as they deserve to be. They now dominate the new generation of scientists in biology. They're very conspicuous in chemistry, and they're now at the 30% stage or so in physics. So things are changing. There are many opportunities for women in physics.
And Natalia is a good student. So good. Okay, Max, it's your turn, please.
What is the importance of non-scientists in the development of science, and how can we reduce the bridge between academic and non-scientist persons?
This is clearly a question of education, and the failure of science has been the failure of education. By the time in America, I'm more familiar with the American educational system than the Mexican. So in my country, mathematics education and scientific education is often compromised. And the reasons for this are many. In this country, there are 10,000 independent school sections, and each of these schools areas can determine the nature of the educational program independently. There's no national guidance about what should be taught. And in particular, in many states, there's opposition to the theory of evolution on religious principles, and there's obstacles to teaching cosmology as well. We know the origin of the universe, the origin of the Earth in particular, took place 4.7 billion years ago, not 4.7 thousand years ago. So there's a lot of dispute between the fundamentalist religious people and the teachers, and a lot of constraints on what can be taught and should be taught. So in the end, education in this country in science and mathematics is not always good. It's usually, my experience at Harvard and Boston University has convinced me that our mathematics and science, our STEM education, is not what it could be and not what it should be. Okay.
That's good, so good. Okay, Eduardo, can you do your question, please?
What does the concept scientific community means?
Well, and that's a bit related to the past question. The scientific community, of course, is the community of practitioners of science, including earth scientists, geologists, physicists, chemists, mathematicians, computer scientists, etc. They have been taught the fundamental principles of logic and mathematics, which makes them able to understand each other. And I can read papers in biology and chemistry and other fields of science with some degree of competence, in many cases, and it's usually the case that chemists and biologists can understand at least approximately what physicists are doing. But most of our people who come out of college who have studied political science or sociology or literature, unfortunately don't understand science, whereas most of the people who have studied science do understand literature and the arts. So there's a bit of disparity. There's too much mathematical illiteracy. There's so much scientific incompetence in my country and also in other countries as well. Thank you.
That's good. Is the turn, Santiago, please?
Yeah, sorry, my internet. Okay. In addition to particle study, what other science subjects make you curious about?
Many things. Right now, I'm very much interested in the study of viruses and vaccines because it's very important that my scientific colleagues in those disciplines solve the problem of the COVID-19 disease. I'm also tremendously excited about cosmology, and I've written some papers having to do with cosmology, with understanding the Big Bang and understanding the evolution of the various objects we see in space, the galaxies, the stars, and other strange beasts like pulsars. Pulsars, for example, are something that was discovered by a woman. Speaking of women contributions to science, we now know what they are. They're rotating neutron stars. The cosmology is another field. Yet another field is computer science and the search for computers that can think rationally. Is that possible? Will there someday be computers that can, well, I once said can beat us at chess, but now they beat us at chess. I once said, could there be computers that beat us at the Japanese game, the Chinese game of Go? And now they have beaten us at those games as well, but they still can't think. But it's a very interesting discipline. Another discipline of great interest is the study of the origin of life. Those of us who do not believe in special creation by God have to have an alternative. So how did life originate on Earth? Well, we haven't the foggiest idea, and that's a very interesting field of research. There are people trying to understand, trying to solve that problem, but we haven't answered that problem. We don't have a good alternative to the religious answer as yet. So there are many other fields that are exciting and interesting.
Thank you.
Good. Interesting person. Do you think we can find other particles that build the fundamental particles?
Sorry, I don't quite understand that. Other particles that build the, yeah, no, I understand. Is there another layer to the onion? We've shown that the atom is made of a nucleus and electrons. The nucleus is made of protons and neutrons. The protons and neutrons are made of quarks. Are the quarks made of something simpler? And I don't think that's the right question to ask. I agree with the string theorists that there has to be another way of looking at things. I don't think the answer is that quarks are made of simpler things. I think that there's a far more difficult question underlying the mysteries that are not yet solved. It's not as simple as finding another layer. It's something else, something more profound, something like string theory.
In future? No.
I don't know what it is. That's for you. I mean, we did our job. We did what we could. We understood a great deal, meaning physicists of my age and even much younger. But it is now up to even younger people to take the next step. So let's hope that the next step is taken by somebody listening to this program, somebody in high school.
Okay, thank you, Doctor. Danny, your turn, please.
Yep. How does knowledge of particle physics benefit human communities and the planet?
Directly, not at all. Indirectly, there are many, many indirect benefits, and the most significant of them is responsible for what we're doing right now. The existence of the internet is due to particle physicists that worked at CERN. The World Wide Web was created for the purpose of distributing data, scientific data, between institutions in different parts of the world. From CERN, where the data is gotten, to universities throughout the world, to 100 different countries. That gave us the World Wide Web, and the World Wide Web has changed everything. Now, there are other examples like this, but the real reason that I do particle physics, and the real reason that many of my friends and colleagues do, is that we believe, as a matter of faith, that it is our obligation to understand the world we were born to as best we can.
Thank you, Doctor.
Thank you, Doctor. Okay, let's go with Natalia, please.
What are currently the challenges of science?
Well, science is a big word. So the immediate one is to find a vaccine for COVID-19. Another is to, less consequential, perhaps, is to understand dark matter and dark energy. Yet another is to avoid another catastrophe which is facing us, which is climate change. And we haven't heard much about climate change these days because we're facing another threat to humanity in the form of this virus. But climate change is really happening, and it is getting significantly warmer. There was absolutely no snow this year in Boston. That doesn't happen very often. We all know that climate change is taking place, and most of us, the scientific community, believes that this is due to us, that we've been doing a horrible experiment. We're digging up all of the carbon in the form of coal and oil and gas and burning it and putting the carbon into the atmosphere. And that is having a terrible effect, we believe. But this country, being as scientifically illiterate as it is, does not fully recognize the danger, and our government, our incompetent government, has pulled out of the Paris Accords, and we are the big sinners in this case. So this is certainly a problem that scientists must address, but it must address with the cooperation of our governments, which we do not yet have.
Let's go, all governments. Okay, Max, please, your question.
Do you think it's important to fail in science, and why?
Important to fail in science. Yes, I did fail a course when I was in college. That I shouldn't have done that. That was not important. But I failed to find the answer to solve the problem that my thesis advisor has assigned to me. Nonetheless, I was enabled to get my PhD certificate, but I didn't solve the problem until 2 years after I had graduated. And even then, I didn't solve the whole problem. Steve Weinberg, my old friend from high school, had to find the other part of the solution to it. So yeah, failing sometimes is necessary. I did what I could do and then put the problem aside, and sure enough, somebody else came along and added the next step to the theory. Yes, each of us does our little bit, and others then fill in the nooks and crannies and eventually build the edifice that we now have.
Thank you, Dr. Eduardo, is your turn, please.
What do you remember about your middle and high school student life?
A good question, and I mentioned a few things at the beginning of my talk, and I'll mention another one. When I was in junior high school, around 7th grade, so I was maybe 13 or 14 years old, they were teaching me about the moon going around the earth and the earth going around the sun, all that stuff, elementary, the structure of the solar system, the names of the planets, that sort of stuff. And I noticed that everyone noticed that you always see the same side of the moon. The back of the moon is forever hidden from people who are stuck on the earth. And to me, that was extraordinarily mysterious, because that meant, in terms of the words that they were using, that the moon is both revolving around the earth and it's also rotating about its axis. And it rotates about its axis in exactly 1 lunar month. That's how it is that we only see one side of the moon. And how could that be? Is this a coincidence? Did it just happen that the period of the moon's rotation is the same as the period of its revolution? And I asked the teacher, what's the explanation for this ridiculously accurate coincidence? And she said she doesn't know. And I was very impressed, because I had asked a question that the teacher could not answer. In fact, I wouldn't know the answer for another couple of years, because it's a subtle answer. It has to do with tides and with symmetry and with many things. But it's a question of resonance. Anyway, so that I knew I was capable of asking interesting questions. The second thing that happened to me while I was in high school, first year of high school, was my attending the talk by the first Japanese Nobel Prize winner in science. That was their first, Yukawa, and he gave a talk, and I couldn't understand a word of the talk, nor could my friends, but we saw the excitement in the front row among all of the Illuminati, the people who knew what was going on, and they were screaming and shouting with words we couldn't understand. And I found that inspirational, and I decided that I had to learn to understand those words. By the way, that was the first Nobel Prize for the Japanese. Today, they have fully 24 prizes in the sciences, forgetting economics and literature and peace. In the biological, chemical, and physical sciences, they have 24. That's a remarkable change and a remarkable accomplishment. So let's hope that Mexico changes from 1 to 24 in the next 25 years, just as the Japanese had done.
Oof. Okay. About this, is the STEM, science, technology, engineering, mathematics program important for the development of scientific vocation?
The program is important. A more important question is, has it been successful? And we talk a lot about STEM, and one of my friends from high school, who's now a professor of physics at retired in Massachusetts has been working very hard on advancing the goals of the STEM program, but it hasn't been as successful as it should have been, as it could have been. It's been more successful in other countries. For example, in Colombia, science education has become extremely good, making use of technologies that have been developed in this country and advocated by the French. They have made use of these technologies and are teaching science much more effectively. Other countries should do the same thing. Perhaps Mexico too can develop better science and technology education. I'm very proud of the fact that I was involved in the first advisory committee for the creation of the Mesoamerican Center for Theoretical Physics in Chiapas. And that institution now exists and now apparently is a quite successful educational institution. That's advanced education in my field of fundamental physics.
Congratulations.
Very exciting new endeavor in the beautiful city of Tuxtla in Chiapas.
That's good. Okay, Danny, it's your turn, please.
Yeah, thank you. Doctor, what do you think about the addition of art into the program making in the STEAM?
I think STEAM is a great idea. I think science, technology, engineering, arts, and mathematics, as long as what you mean by arts is the art of writing, the art of speaking, and the art of logic, usually known as the trivia, the three important ingredients to a medieval education: thinking, writing, and speaking. Now, what about the fine arts? Well, for the fine arts, there are museums. You can go to museums and look at pictures. You can go to concerts and hear music. You can go to operas and hear operas. So the arts can be well taken care of by our museums and our concerts and such. But I don't think they have to be included in the fundamental education. It's already enough to teach what we're trying to teach. STEM with an A, STEAM with the arts of rhetoric, grammar, and logic would be a good beginning. Thank you.
Thank you, Doctor.
Thank you so much, Doctor. Thank you so much, Maggie, for conducting these questions. We're going to proceed with the panelists, and then after that, we're going to do the Q&A that have been submitted. But before we do that, let me launch a quick polling. We're going to do a little trivia questions, talking about trivia, Doctor. So there is a question on your screen. That is a trivia question. You can just take a minute to answer that one. Or okay. Only for the attendees.
All right. It's not for us. Sorry.
Yeah, because all of you guys know that. Sorry. Okay, gonna end the polling.
Better organized.
Okay, gonna end the polling, and okay, so most of the people answered correctly with physics. A couple of them are. Yeah. Okay, so we're gonna continue now with a panelist. Pelagius, can you please open your camera and microphone?
Yes, thank you. Thank you so much. Student Mauricio Barroso Jimenez, please ask your question.
Hello, Dr. Glashow. When you started studying physics, did you ever think about winning a Nobel Prize?
Did I ever think about winning? Not really, not until perhaps the year before I won it. You don't get anywhere by aiming toward winning a Nobel Prize. What you aim for is doing science and doing it as well as you can. If you focus on winning a prize, you will be causing yourself a great deal of disappointment, because there are more great scientists than there are people that can win Nobel Prizes. There are many people who deserve Nobel Prizes who don't get Nobel Prizes, And there are many people who do win Nobel Prizes who don't deserve to have Nobel Prizes. So you don't spend your life worrying about a silly prize that the Swedes have invented. You worry about doing science as best you can.
Okay, thank you.
Thank you, Mauricio. Student Juan Carlos Galina Migueles, please ask your question.
Hello, Dr. Glashow. My name is Juan Carlos, and for me it's a great honor asking a question to a Nobel Prize. This is my question. What advice would you give to those who like physics, but sadly, they have to think about studying abroad due to lack of opportunities in Mexico?
Yes, that's a real question. Well, in order to become a competent theoretical physicist, you would certainly have to spend some time abroad studying with people who really know the field. There's no question of that. But then you could come back to your country and pursue theoretical physics, which is not a very expensive discipline and doesn't require accelerators and such. Now, your country has invested in experimental facilities. I know when I was there in 1955, the Autonomous University of Mexico had built a very fine Van de Graaff accelerator. And it was newly installed. I don't know whatever became of it, but are there Mexican physicists working on experimental physics at CERN? I believe the answer is yes. I can't name them offhand, but the wife of my colleague, my one-time colleague, I mentioned my Italian colleague, what was his name? Anyway, his wife is also a physicist and lives in Mexico. He's married to a Mexican woman, and she is a very skilled theoretical physicist, and she's living here. Imagine there are opportunities in this country.
Thank you, Doctor.
In your country. There should be. Lord knows there are a lot of very bright Mexican students I met on the many occasions I've come to Mexico. I was surrounded by many men, and mostly men, some women, who were very talented and very skilled in what they were doing. And they have, the brightness is there, the intellect is there. Maybe there aren't as many opportunities today as there should be. I hope in the future there will be more. One of them is this institute that is created in Chiapas.
Thank you, Doctor.
Thank you, and thank you, Pelayo, as well. I'm going to launch another poll very quick, and this will allow also the panelists to vote.
I voted, but I know. I know I'm right.
We got a few more seconds. Perfect. Thank you so much. I'm gonna publish the results. So these are the results. Most of the people knew that you were awarded in 1979. Thank you. So now we're going to proceed to answer the questions that were submitted through the Q&A button during the session. the way we want to do it, we want to provide the microphone to the people who is connected and who made a question, and then you can verbalize your question directly to the doctor. So, Luis Santa Maria, can you unmute yourself? And ask your question.
Yes. Could you explain, please, the G-force?
Perhaps the Second World War, when there were airplanes would have dogfights with one another over Britain during the Battle of Britain in the 1940s. And when you make a very steep dive, as you do if you're a German pilot in a Stuka dive bomber, you are subject to very severe forces as you make these rapid movements in space. And when you say you suffer a G-force of 2G, that means that the weight, you're feeling, you feel as if you have a weight of twice your normal weight. And if you are exposed to a G-force of 10 or so, the force is so great that it will probably kill you. So this is just the result of acceleration. When you accelerate, you sense a force, which is not truly a force, but it's a reaction to the fact that you're accelerating. When you're in an elevator, when it accelerates up, when it starts going up, you feel heavier. And when it comes to a stop, you feel momentarily lighter. Those are G-forces, as is the force you feel when you're in a car that goes around a steep corner and you are pushed to the outward from the center of the arc in which you are traveling. These are all not real forces. They are merely the reaction to accelerated motion.
Okay, please, what is the measure of the G-force?
What is the what?
The measure.
I don't know. The G-force is just a consequence, is just a simple consequence of the theory of motion that was developed by Newton 400 years ago.
Okay, thank you.
Alejandro,
yeah.
You can proceed with your question, please.
Thank you. Good morning, Doctor.
Good morning.
It's nice to see you. I hope you're having a good time. My question is, if you would be able to be a physicist, what profession would you choose that makes you happy, and why would it be that one?
Well, let's say if I were not a scientist, because I could have been an astronomer or a mathematician or a chemist. I was very fascinated by chemistry at one point in my life. I have a favorite element, which is selenium, and I did a lot of work on selenium. But something different. Well, I don't know. I wouldn't have been very good in the profession my father had. He was a plumber. I don't think I'd like to be a dentist the way one of my brothers was. And I don't feel that I would have liked to be a doctor because I wouldn't, especially a surgeon, as my other brother was. Perhaps a psychiatrist.
Oh, okay.
Let me make that guess.
Aldo, are you on mute? Aldo?
My question is, when you was a kid, you imagined that in the future you will be a Nobel Prize of Physics?
No, I never gave it a thought when I was a child. All I wanted to do was to understand what other people had done before in the field of science. I hoped when I was in high school that I would become a professor at some good university. But at that time, I didn't even know what a good university was. I doubt that I even heard of Harvard where I ended up being a professor for 30 years. No, it's not. I certainly didn't aim for the prize. It's not like athletes who dream of winning the Olympics, which you can really strive toward because there's a definite numbers involved. All you have to do is do some physical feat better than a certain number, jump higher than X or run faster than Y. But there's no such principle in academic research. You just want to do whatever it is you think you can.
Okay, thank you.
Thank you, Professor. I'm asking Jaime Gomez to unmute, but Jaime, can you proceed, please?
Yes. Hi, doctor. How are you doing? Speaking about renewable energies, what is the principal challenge the humanity will face in the short time to apply them, reducing the use of non-renewable energies?
Non-what? The use of what?
Non-renewable energies.
Jaime, I didn't quite understand. Maybe try.
Yes. Speaking about renewable energies, what is the principal?
Renewable energies. Oh, yes. Okay. You mean alternatives to burning fossil fuel? Well, clearly, the world must stop using oil and gas and coal. That's not happening yet, but it can happen if we switch to, as we are, to solar and wind in large measure. But it cannot just be solar and wind because the wind stops from time to time and the sun stops every night. And also the sun goes behind clouds in the daytime. It's a very irregular source of energy. As is both solar and wind. What we need is clearly nuclear as the standby background source of energy. Now, nuclear energy and fission energy is specifically what I mean, because fusion energy is not within sight at the moment, not within the next 50 years. So it has to be nuclear fission. And right now, the prejudices against nuclear fission are very strong. Germany is turning off its nuclear plants and replacing them by coal, of all things. Japan, having had a severe nuclear accident some years ago, is now increasing its dependence on coal. So these countries are going in the opposite direction from the direction in which they must go in the future.
Thank you so much, Doctor. Janet and Lizette, can you proceed with your question, please?
Yes. Hi, doctor. How are you? I want to know if you can tell us, how do you think a kid becomes as enthusiastic as you in science?
Say again?
That we are wondering, like, how do you think a kid becomes as enthusiastic as you in science? How do you think that the kids can become like you have that enthusiastic?
Well, I don't know exactly why I became interested in science. In part, it was because of my scientifically inclined friends. We had common interests. I developed an interest in science through science fiction, and then I found other kids who also read science fiction who were also excited by science fiction.
Okay.
So that was one direction, and another was simply by observing what all of the advances that were taking place, the appearance of television. I mean, the replacement of propeller planes by jet planes. All of these things indicated that science really can do some interesting things.
Okay, thanks. Then it's a good thing to think about it. Thank you very much.
Thank you, Lizette.
Good morning.
Jenny Hidalgo, can you proceed with your question, please?
Yeah, thank you. Good morning, Professor.
Good morning, Jenny.
I was studying something about the brain. After so much study and research, have you ever come up with answers through dreams?
What the
Yes, by sleep, while sleeping, certainly, while swimming. I remember having some good ideas while swimming in Acapulco many, many years ago in the 1960s. Yes, that's a nice thing about my field, is that you can do research under very relaxing circumstances, while on vacation at the beach, while on a boat, and yes, also lying asleep, unable to sleep, but doing physics nonetheless. Sure. The good thing about theoretical physics is you can do it anywhere, in any place, anytime.
Thank you very much.
Thank you so much. Regina, Korea, can you proceed with your question, please?
Yes, hello.
Hi.
So I wanted to ask, there are formulas in quantum physics, well, I don't know the formal name, such as like Banach-Tarski and wormholes. And my question is, do you personally think this could happen or have happened in real life?
There's no indication that these things called wormholes exist in reality. They exist in the context of various theories that are not descriptive of the universe that we live in. So there are many speculations about strange things, but there doesn't seem to be any likelihood that we would ever experience such things as wormholes in our universe. So no, the human imagination is unlimited, and we, some of us study all manner of things. We study black holes, although we can never get near them to verify that what we say is correct. But we now know that black holes really do exist, and we have good evidence. We've heard them collide with one another in space. That's a very exciting development that has just happened in the last few years. A new branch of science, gravitational wave astronomy. It gives us another window into the universe. It's not a wormhole, but it's another way of understanding nature.
Okay, so they're just like mathematical like expressions.
That's right. That's right.
Thank you so much, Regina, for your question. And we will come back to you for the next one, but now let's go to Lopez Acevedo. You unmute yourself, please.
Yes, thank you. I would like the professor to explain me which is the relationship between the dark matter and the neutrinos.
Between dark matter and neutrinos, the relationship is very tenuous. If neutrinos had masses 50 times higher than they do, 100 times higher than they do, they could have accounted for the dark matter. But neutrino masses have been shown to be very small, so small that they, although they do contribute to the dark matter, they only contribute a few percent at most of the necessary amount of matter in the universe. So it is not neutrinos. We know that for sure. It has to be something else. And what that something else is, we do not yet know. But we do know that it's not neutrinos.
Thank you.
Thank you so much. Can we continue now with Regina, with your next question, please.
Oh yeah, thank you. So my question is, what do you think that it's the next step in terms of education and scientific research technology in developing countries such as Mexico?
What's the next step? In order to answer that question, I would have to know much more about education as it is today in Mexico. I'm afraid I don't know the answer to that question. I have made only very brief visits to Mexico over the past few years. I only visited Chiapas twice in my life, for example, and Mexico City maybe half a dozen times. I don't really have a feeling for what education is like. One of my mentors in college, who was at the time a graduate student at Cornell, I was a mere undergraduate, emigrated to Mexico. He went to the university at the Veracruz and became a very valued member of the computer science department at Veracruz. I understand that their level, scientific level, is very high. But as to education in high school, I know virtually nothing. This is the first high school that I've spoken to in Mexico. I've spoken to a number of high schools in America where I find that science education is weaker than it should be, and mathematics education is very much weaker than it should be. I don't know the status of mathematics education in Mexico. I don't know if you do well in national exams. I know that the United States does not do all that well in international comparisons with other countries, and the countries that do well tend to be countries like Singapore or Finland, and not the United States or Britain. What are things like in Mexico? I don't really know, so I can't give advice in that direction.
Well, thank you so much.
Thank you, Doctor. This is Janet. Can you proceed with your question, please?
Yes, thanks. Doctor, this is two questions in one. It's like, what did it feel like to be recognized as a Nobel Prize? Did it make any difference to you, to your research?
That's a good question. And firstly, let me say that my best research, my most exciting research was done in the 1970s, prior to winning the Nobel Prize in 1979. And nothing I have done since compares in excitement to what happened in the years between, let us say, 1974 and 1978, something like that. Those years were full of excitement every day. It would drive my wife crazy that so many things were happening so quickly. Afterwards, things were different. I still did some really, I think, good research afterward on testing Lorentz invariants, on the possibility of antimatter, matter symmetric universe, things like that, but nothing so exciting. And I don't think that's the fault of the Nobel Prize. I think it's the fault of having been too successful earlier, and all of the low-hanging fruit had been taken, and the remaining problems are too hard.
Oh, thanks. It's good to know that. Thank you very much.
Thank you so much, Lisa. Marcela, can you please unmute yourself and ask your question?
Sure. Hi, Dr. Glasgow. You said
Hi.
You learned more from your classmates than from your teachers. What advice could you give us to seek knowledge creatively in a non-traditional environment?
What kind of non-traditional environment?
just like out of the class, maybe, you know, when you said you were in the subway and when you said like in common places, how do you keep thinking and looking for more things?
Well, the amount of time spent in the classroom is relatively small. So there's lots of time left in the evenings and during the day when you're not at school to think about physics, to read about science, to learn things that you were not taught in school. I would buy college textbooks while I was in high school and try to learn things from them. I would buy college preparations books for mathematics and for calculus. I would sometimes take summer classes. I would read books about scientists and about science. So much you can do outside of school. Go to a library and read the biography of famous scientists.
Thank you.
Thank you so much, Doctor. Juan Carlos, can you proceed with your question, please? Carlos Castillo.
Yeah, hello, doctor.
Hello.
It's nice to talk to you. I have a question. I'm a parent, I'm not a student. You know, right now, in the actual days, kids have so many possibilities. They can go for arts, they can go for social science, they can go for anything they want to choose. But my question is, how can we encourage right now to our kids to go for science? Because they have so many options. What can we do as parents?
Yes, well, as you've mentioned, that Mexico has not been as economically successful as it should be. And so the number of opportunities for a young person are fewer than they should be. And it is essential, of course, to aim toward a profession in which you can support yourself and your family, as well as following your interests. Fortunately, in my case, I had no insuperable difficulty. I was born in an upper middle class family, and I went to the public schools in New York City, which at the time were very good. I went to a semi-public university, Cornell, which is a land-grant university and is partly public and partly private. I was fortunate to be supported in graduate school by the National Science Foundation. They paid my tuition and gave me living expenses, which I made it easy for me to attend school I didn't have to be burdened by teaching at the same time that I was learning. I regret that to an extent because I probably would have become a better teacher if I had to become a teacher earlier. But the National Science Foundation in my day, was very supportive. Is there an analog to that that offers undergraduates or graduates financial support in Mexico? Is there a Mexican National Science Foundation that offers financial support? I don't know. There should be, but there may not be. I don't really know.
Okay, thank you very much, Doctor.
Yes, I think there is CONACYT. There is an institution that provides some scholarships for advanced in science. So you need to get a commitment as well with them for master's degrees and PhDs. Yeah, thank you for the question. Jaime, could you proceed with your question, please?
Oh, yes, this is a weird question or strange question, but I had the doubt. Doctor, could the COVID-19 virus be created in a science laboratory?
Could it have been created in a science laboratory? Technically, it might be possible. There is no indication that it was. There there is a laboratory for virus research in Wuhan, in China, and there are American scientists who have participated in that research. It's been very valuable research. There was no attempt to create new viruses there. There was every attempt to try to understand the nature of the viruses that exist among the bats in China. We know that viruses very, very similar to the SARS virus and this virus, the COVID virus, do exist among the bat population. And the mystery is how those viruses adapted to become diseases of people. And it is suspected that there was an intervening animal that got infected by the bat, which then at the open meat markets in China managed to spread to humans. But there is absolutely no indication, as has been accused, stated by some people in my country and elsewhere, there is no indication that the virus that has infected us all was created artificially. Had that been done artificially, there would have been an indication of it. There is no such indication.
Thank you very much, Doctor.
Thank you, Doctor.
Understand how dark matter is made of and how it behaves?
Yes, we'd like to know the answer to that question. We can't discuss how it behaves until we understand what it is. Is it a particle? That's one possibility. Such particles have been called WIMPs, and specific theory of such particles had been suggested in the form of supersymmetry, but those supersymmetry theories have been excluded by experiment. It could still be a very heavy, weakly interacting massive particle, as some people believe, and many experiments have been done to search for such particles, and none have been successful. Or it could be what are called axions, which are very light particles that have a relationship to elementary particle symmetries that were suggested by Frank Wilczek. Those particles are very difficult to detect. Many experiments have been done. None have yet been successful. Very sensitive experiments are planned in this country, in America, and also in China, but everything has stopped for the moment because of the virus. Someday that will change, of course. I hope that one day we will identify the nature of dark matter and explore its properties. Of course, in the process of detecting it, we will learn some of its properties. If it's a heavy particle, it will collide with other particles and produce observable signals. And if it's an axion, those axions can be detected and studied, but we don't know. It might also be that some people argue that our understanding of gravity is incomplete and that there really doesn't exist any dark matter at all. It's an illusion resulting from our failure to understand gravity. I don't think that's correct, but some people have that belief. There are many possibilities. It's a mystery. It's a mystery that must be solved, but it has not yet been solved.
Wonderful. Thank you for the explanation, Doctor. And then finally, the last question is Regina. Can you make your last question, please?
Okay, hi again.
Hello again.
So my question is, what advice would you give to someone who wants to be like a science researcher, scientist, and just like devote themselves into science?
Good question. Well, one thing depends on how old you are. at some point as early as possible, you should choose what field of science you want to go into. There's so many different fields ranging from geoscience to astronomy to medical science to biological science to earth science to sciences related to climate change, climate science, particle physics, condensed matter physics, thermodynamics, or chemistry, psychology, computer science. There are an endless number of different sciences which require different preparation. Many of them in the physical sciences require a profound understanding of mathematics. Most all of them require a knowledge of calculus. Most of them require a knowledge of computer science, some of them which involve large quantities of data like particle physics, experimental particle physics, or climatology, or library science, require the understanding of how to handle enormous amounts of information conveniently. So that it depends on computers. So first identify what your interests are. My wife's sister, who is no longer alive, unfortunately, was her name was Margulies. Lynn Margulies was a famous biologist, and she won the President's Medal of Science. But her work was never accepted until she became quite old. For many years, she was regarded as somewhat of a nut with her ideas of how complex organisms evolved. But she's been proven to be correct and is now regarded as the founder of our understanding of the development of complex organisms. We all result from infections by bacteria. Were it not for bacterial infections, we would never have become what we are. Strange hypothesis, but one which turned out to be correct.
Wow, that's amazing. Thank you so much.
Thank you so much. We are running out of time, but there was just one last question from Aldo Quiroz. What do you think is the key for success?
What is the recipe for success? Yes, well, take 1 teaspoon of brains and 3 tablespoons of hard work and a glass of love for your discipline, and put them all together, drink it, and win your Nobel Prize.
Excellent. Thank you so much, Doctor. So thank you, Doctor. We're going to proceed with the last trivia question. They're going to go give the microphone to Arturo and then to thank you. Please just we want to have a few more minutes to wrap it up. So also all the panelists are allowed to answer the question and encouraged to answer the question, please. As you answer the question, you probably can see that there is a reference there. You can find out all the different articles that Dr. Glashow has written recently. So, okay. So this is how it's answered. We encourage you to go on and review the articles from the Dr. Glashow and move on to Arturo. Can you turn on your camera, please, and your microphone?
For wrapping up and finishing, I would like to thank Dr. Sheldon for taking the time to join us and share some of his life achievements and thoughts. It's been a privilege to listen to you. Dr. Shapiro, Thank you for being so close to us and for your great attitude to serve and to help. Manuel and Mauricio, thank you again for everything. For Colegio Castlefield community, it was an honor having you with us. Thank you to our panelists for your enthusiasm. Thank you to everyone involved in this project. It's been enlightening and enriching to have the opportunity to listen to a Nobel laureate. For those who took the time to join us, also thank you. Colegio Castlefield will always be looking forward to have events like this. Manuel, thank you very much.
And thank you for the privilege of being in Mexico once again, even though it was remotely.
Thank you
so much, Dr. Glashow.
Be back soon.
Thank you so much, and thank you everybody for your attendance, and we look forward to stay in touch, and thank you Ed for your friendship and Dr. Glashow for your time. Arturo and Mauricio for being hosting us. Thank you for the panelists that you take the time to go that in detail and for helping us to guide. Thank you, Pelayo, also for the opportunity, and we encourage all the attendees to become one of the scientists. Hopefully we can listen to you in the future when you share another success stories.
Absolutely.
Thank you, everybody. Have a wonderful week. Stay healthy.
Thank you, everybody. Have a nice day.
Very best.